know what codechromy is. I hope maybe not. Okay, here we go. So for those who haven't watched the day 2 video, here's an introduction to what we're doing. You have in this pink packet, as well as the buff sheet, just all you have is just a huge list of different functions. Okay, like there's 30 different functions here. There's 59 different functions on the buff sheet. And all those functions are formulas for finding lists of XY pairs. We've talked about that since day 1 in this class. That formula over there, I can do it by hand, or I could use a calculator to make it a lot faster, and I can make a list of XY pairs. If I make the list of XY pairs and I create a graph, the graph will have some sort of appearance. I don't really care that much in this class what the graph looks like. So just pretend that this is the graph. Okay, it's not, but pretend that it is. Like pretend that what we are looking at, let's get the marker here. Pretend that we are looking at the graph, y equals, get a better color, y equal, what is it, 1 over 2x to the negative 4? Is that right?
Yeah.
Thank you. And I wish I could give a compliment to who told me. I can't remember who it was. It might have been Dalvin, actually. I had a bad habit in the videos referencing things by pointing, which works really good for all of you, but those who are at home watching the video, like, what is he pointing at? And so if you see me like underlining and retracing and boxing incessantly, it's my attempt to make the video watchers at home not get lost. So, yeah. If you see me, but if you think of something else I can do as well, speak up. Like, let me know, hey, wait a minute, when I was watching the video, that was hard for me to follow. Just tell me, okay? I spent 15 years working for a small company, so I am very customer focused. Like, my focus is, you are my customers. I want to do all I can to help you be successful. So, we good?
Yep.
So imagine that's the graph. We would find all the points using the formula. The task today is to come up with a new formula. The new formula, instead of being y equals something, the new formula is going to be this. dy dx equals something. And we'll cheat here just 1 second. Is that one of the answers on the pink sheet?
Yeah.
Yeah, so that's what we're trying to get. Okay? So we're starting with this formula. We are trying to create the green formula. The pink formula is how we calculate all the XY pairs. The green formula is the derivative of the pink. That means the green formula is how we find the tangent slope anywhere on the pink. That's what we're doing in Unit 2. Ariana, please. So what Ariana said, and I need to do better at this as well, I tend to not restate the question. She asked if dy dx is the same thing as y prime. The answer is yes. Simply 2 different symbols that mean exactly the same thing. And in fact, if we were to call this function f of x, so 4 points for Ariana. I have to give more points now because I only see you half as often. If we called this f of x, then we could call this f prime. And that's what we talked about in Unit 1, is like, what was f prime? What we didn't do in Unit 1 is we never created an f prime. They just kept giving us f prime. Now we are learning to create f prime. That's all that Unit 2 is about.
Are we going to use these same rules to find f double prime later on?
So what Dallin said was, do we use the same rules to find f double prime? I'm going to get you to answer the question yourself.
Yes.
The answer is yes. Here's why. That came out all wrong. we learned in Unit 1 that if you understand how f relates to f prime, you really don't have to learn how f prime relates to f double prime because it's identical. So yeah, same thing. Everybody else? 4 points for Dalvin. Okay. What you need to realize is the way that we actually calculate this, the way we calculate this Dydx formula is we technically look at the graph and we say, okay, I want to find the slope right here at that point. I want to find that slope. To find that slope, I go find a nearby slope. I create a secant line to the left, like this, and I figure out a way to calculate the slope of that secant line. So that's what the computer is doing right here. The computer is calculating the slope of that. That's cool, look at that. It moves with me. Calculator is mesmerizing, hypnotic. Okay, that's annoying, you're all saying stop that. So anyway, so I find a secant to the left. I do the same thing to the right. That's this one. Then I zoom in. I make those secants as short as possible. Ideally, infinitesimally short. And what that allows me to see is the slope right at that point. It's got to be somewhere between those two secant slopes. If you zoom in far enough, this secant slope will become something like 10.0000 whatever. This secant slope will become something like 9.9999999 whatever. Questions?
Are those just random numbers? Like the 10 and the 9?
Random, well, it's just a specific example. So for this exact, what Maggie said was, are these numbers random? What they really are is for this specific graph, if you literally zoom in on this graph, that's exactly what you see. So they're actually not random at all, they're just specific to this example. What we're trying to do is apply the same idea, 4 points for Maggie, to pretty much any function. But the idea doesn't change. The numbers will change. But it's not about the numbers, it's just the idea that if I want to find the slope at a point, the way I'm going to do it is by finding the secant slope on one side, the secant slope on the other side, and then making them very, 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 very short. That's the idea. Questions? Okay. Now what's weird is, I'm going to show you a method for doing that. We're literally finding secant slopes on both sides, making them, as Caitlin just said, infinitesimally short. Okay? But the method I show you doesn't appear to resemble this at all. It's because there are several steps in between this idea that you see on the board right now, this idea, and the method I'm going to show you. And those steps that are the in-between steps, they're not tested on the AP test. So I don't feel it's worth our time to be spending a lot of time helping you understand those intermediate steps. It just takes too long. So it may not feel like we're doing anything with this thing here. We actually are. We're coming up with an equation, we're finding the slope, and it is found using this method. Just you're missing the intermediate steps. The rule sheet I gave you is a list of shortcuts. And the shortcuts are so well designed, you kind of lose track that we were ever doing this. But I need you to remember that we did this because they do have a few questions that ask you to kind of link the two. Questions so far? Okay, so let's start doing the problem now. Okay, here's my formula. I want to find the formula for dy dx. Here's how I do it. Basically, you must have good notation in this unit. Last unit, we kind of drifted away from notation because it was like looking at graphs. There really was no notation. This unit, my warning is, if you come to me at the end of the unit and you say, I did really bad on unit 2, test 2, I need to retake test 2. first thing I'll ask for is your 3-ring binder. I will look at your work for Unit 2. If I don't see that you used exactly the notation that I used, you don't get to retake Test 2. Because this unit is so heavily dependent upon good notation for success, that if you spend 3 weeks just writing down garbage, that's clearly why you did bad on Test 2. And I can't let you retake. You're done. Like, you have to have my notation. Don't do any writing on the handouts. You're going to do all your writing on separate paper. So nothing gets written here. This is just like a textbook page, just where you find the problem. So everyone should have paper in front of them, and you need to be writing exactly what I write. So for example, first thing, you must always rewrite the problem on your paper. You're going to write y equals 1 over 2x to the negative 4. Okay, now this particular problem has a little trick to it that you sometimes use, sometimes you don't. So when to use it, you'll kind of learn by experience. For today, I'm just going to tell you the trick. The trick is that I can easily make this into a much simpler problem. So I'm not doing any calculus yet. I'm just reviewing some algebra. Questions there? Just separate the two fractions. Again, just reviewing some algebra. So now I have y equals 1/2 and then x to the 4th divided by 1. Which means I really have y equals just 1/2 multiplied by x to the 4th. Questions? Please, Kenny.
On that, you just did a reciprocal, right?
Right idea, wrong word. That's okay. Basically, I just took advantage of this property, which is related to reciprocals for sure. The property says that 1 over some base to some exponent is exactly the same thing as that same base raised to -1 multiplied by the exponent. That's all. So I'm just using a rule from algebra. 4 points per case. Anything else? Okay, now we're ready for calculus. Remember, the goal here was to find a formula for computing the slope of this function at any point. So I want a formula that's called dy dx equals something. So just write down on your paper that that's what you want. Like literally say, hey, here's my formula for y. Well, I want to take that formula and I want to create a new formula. So you just tell the grader what you're creating. You're creating dy dx. Questions? Cool. Now you take advantage of the most important part of this class, the equal sign. You say, hey, I have a rule sheet. Oh, no, not yet, sorry. I take advantage of the fact that y and this expression are exactly the same thing. So dy dx must be exactly the same thing as d of this thing, because this is also y. So I just put that in place like that. That needs to make sense to you. If that doesn't make sense, talk to me so we can help you feel good about it. But all I did was recognize that I want to find dy dx right here. And because y is, as stated, 1/2 x to the 4th, I can write on this side of the equal sign d of y. Just using a different version of y itself. So that's why that statement is true. Okay. If I had a computer, I would be finished. I can take this formula right here, put this in a computer, and that computer will tell me the slope at every point of this function here. Okay? No problem whatsoever. However, on the AP test, you got to do 2/3 of it without your calculator. So they expect you to understand how to do this without a computer. That's why we have the rule sheet. So we want to transform this formula from a computer-friendly version to a non-computer-friendly version. The way the rules work is you have to go find a rule that looks like what you see here. And it must be an exact match. So the rule that matches in this case is right here. Let's make this a little bit smaller. It's the multiplying constant rule. So I'm going to copy the rule over just to make it easier to talk about. So multiplying constant, come back here, paste that in, and notice how it's important that you can see clearly that we have a perfect match. The way we identify the match is we notice that this says d over dx, d over dx. The rule says d over dx. The rule talks about a multiplied by some f. All I have to do is correctly identify a and f, and now the rule will match. So I want to figure out here, what should I choose a to be, what should I choose f to be, so that this box ends up matching this rule. Like I want that, do different colors here. I want that maroon box to match this blue box. I make the match work by simply choosing a correct value for A and a correct value for F. I'm not trying to ask a simple question. I just don't want you to overthink it. Just raise your hand and tell me if you know what A should be and what F should be so everything matches. It seems simple. You're right on target. It's not supposed to be hard. Say, so as long as I can identify that A should be 1/2 and f of x should be x to the 4th power, this box in blue will be exactly the same thing as this maroon box up here. How many knew it? Show me. 4 points. Okay, 5 for Sadie. Questions? Now we take advantage of this again, the equal sign. We say, okay, the rule tells me then that instead of using this non-human friendly, it's a computer friendly version of the formula, let's go replace this with its equivalent. Equal means the same. So I'm going to make a replacement. I'm going to plug this in place of this. Question? So let's move it out of the way so we can do that. So on the next line, you're going to write dy dx. Again, make sure you have exactly the same notation that I have. Equals. I'm supposed to write down a, so I do. I'm supposed to write down d over dx of f. So I do. D over dx, and the f that I have selected in this case is simply x to the 4th, like so. Questions, concerns, curiosities, anything? Awesome. Okay, what you should be noticing is, another way to think of what's happening is to say, okay, the first thing was I ended up with what I call the derivative operator. That's d over dx. And that derivative operator is operating on the entire function, all of this. But as I start using rules, what happens is the derivative operator starts working its way inward. like it's consuming, it's kind of a way to say it, but it's like working its way through the entire function. Notice how on this blue line, our derivative operator over here, ddx, is no longer operating on all of the function. I guess an easy place to see it was here. It's no longer operating on everything. ddx is only operating on x to the fourth. So I'm working my way into the function, like from outside inward. Questions? And also, don't lose track of the final goal. The final goal is to get a formula for dy dx. Well, I actually have part of the formula finished. See, this part is now non-computer friendly because there's no ddx term in it. I still have to work on this part, but I am partway finished. And that's how all of these, that's how this process always works. Unit 2 is the simplest unit to understand because it's just the same process over and over again with different functions. So all we're learning to do is one idea for a lot of different examples. Okay? Now I need to figure out this one. So I need another rule. I need a rule that looks like this. That rule happens to be the power rule. So let's go copy that over. See, that's up towards the top of the page. So here's how I know that the power rule works. Pull it down. And just now what I have to do is I still have the ddx, so that's easy to see that those are the same. Here's d over dx. Here's d over dx. Here I have some g. And I have some n. As long as I pick g and n appropriately, this orange box will be an exact match with this red box. No reference to the video company. So, questions? So again, just giving away points. Raise your hand and tell me what g is, what's n. And what's g and what's n? Madison?
G is x and n is 4.
So g is simply x. N is 4. Who knew it? 4 points, 5 for Madison. Please, Jacob.
So how do you know which rule to use when?
Say again.
Which rule to use when?
Got you. So what Jacob said is, how do you know which rule to use and when to use it? It really becomes, for lack of a better word, it's like a menu. Seriously. And you're going to start out by using the menu, looking at it. But then with experience, the menu just kind of migrates internally. You don't have to look at the list any longer. But you're simply looking down the list for a visual match. Like I look at the red box, and then I look at my menu, and I think, okay, what do I have here? I have ddx of x to the fourth. So I look at the rule list, and I'm going to skip power. We know that's the one that works. I'm going to show you the ones that don't work. That'll help you see which one does work. And I say, well, let's see. Let me get a pen here. I do not have ddx of e to some thing. Like that just doesn't fit. So that won't work. I come over here. I don't have ddx of ln of something. I don't have a square root. A is just a constant. I don't have that either because remember, I've got x to the fourth, not a constant to an exponent. So that means this rule doesn't fit. I don't have any of the trig functions. They don't fit. It's just a menu. You're just looking for what fits. This one fits. remember, g of x can be anything. That's your choice. So I'm choosing in this case to say, well, as long as I let g of x equal x, and I let n equal 4, hey, that matches. So that's the rule I pick. In most cases, there is only one rule that will work. If you choose the wrong rule, you've somehow looked at it incorrectly, and it's not really matching like you thought it matched. 4 points, Maggie.
So if x was a number, then it could be that one, the exponential rule?
So if I were working the problem, here's what Maggie asked, and I had something like this as I'm doing my work. Something like that. I would definitely stop when I got to this spot on the rule list. I'd say, oh, look here. Oops, wrong button, hold on. I'd go right here and say, this is going to work because in the one I just showed you, if I choose a to equal 5, and I choose g of x to equal, what was it, x subtract 2, now I can see that the exponential rule does fit.
So there's the power rule, but for that too, because g of x could be, or can g of x only be.
8 points for Maggie for asking 2 really good questions right in a row. She's asking, will these seem like they're kind of the same thing, just depending on how I make my choice? What's restricted here is the a has to be a constant. It can't be some sort of expression involving x or y or t. It has to be just a constant. So in the problem we're working on, the exponential rule wouldn't work because x is not a constant.
Yeah.
And then on the power rule, the n has to be a constant.
Okay.
Does that make sense? That's how I keep those two separate. Does that answer your question? Perfect. Anybody else? Awesome. So come back here. Way too many buttons on the board now. So I'm going to use the power rule. Here's what I know I need to use to make my substitution. So again, you just use the equal sign and make an equivalent replacement, like that. And keep in mind, we're doing one example. We're kind of getting very deep and trying to answer all your questions so you make sense of it, which is crucial. Really, other than a few algebra tricks you sometimes run into, once you know the process for one problem, it's the same process for all the others. It's just different rules. Yeah, please.
So are we always going to have to use multiple rules for like finding a solution?
Pretty much every problem they give you for this class, you will end up using at least 2 rules. Depending on the problem, 3 or 4. Not typically more than that. Although they could invent something that was worse, but they just really haven't. It's like any test, they have to put a restriction on how difficult they make it. So anyway, 4 points for Max. There we go. Okay, so back to here. Let me get some stuff out of the way. So let's see. Let's move this stuff. That didn't work. We'll just erase it. That's not the right erase I wanted. I want to just get rid of this. So using the power rule, the next line, get some space here. Pull these out of the way. The next line is going to say dy dx. Or get used to the fact that we can use different symbols that mean the same thing. That's good preparation for the AP test where you don't know what symbol they'll use. So we'll use y prime now just to switch it up. Got 1/2. Now I need to write down n. N in our example is 4. I've got to make sure these show multiplication. If you get used to using more parentheses than you ever used before, I promise you will do much better on the test. It just saves you from mistakenly thinking you're adding or subtracting and reminding you that you're multiplying. So I have 4. Now I need g of x. G of x in this case is just x. So another set of parentheses there. I need an exponent. N subtract 1. N is 4, so this exponent becomes 4 subtract 1. I need to put d of dx of g of x. So that's d over dx of just x. Like that. Questions? Okay, again, notice how the derivative operator, we started out operating on the entire function. When we used the multiplying constant rule, we switched to having ddx of just x to the 4th. We now use the power rule. Now we just have ddx of just x. Like we've burrowed all the way into the problem. Okay? You get to this point, you know you're finished. Because dx over dx is 1. Multiplying by 1 doesn't do anything. There's no longer a ddx operator anywhere. We just have the formula. dy dx. Do a little math. 1/2 times 4 is 2. X cubed. So as I promised when we began, that is the correct answer. This was a correct answer as well. It's only useful on my calculator or computer. This is more useful. I can do some analysis without the computer. So, please.
Well, like, I don't know if you can ask, but is there going to be more than 2 rules that you will use?
Gotcha.
Most of this because there's
going.
multiple steps that you have to take.
Yeah, it will depend on, so what Caitlin asked was, in this particular problem, we ended up using only 2 rules, the multiplying constant and the power. That will just vary from problem to problem. The multiplying constant is used very regularly in many problems. It's a really easy rule, though, because all you do is recognize that if you have, like right here, ddx of a multiplying constant multiplied by some function, you just pull the constant out of the ddx. So that's a really simple rule that gets used all the time. Power rule is very common as well. I'd say more common to use 3 rules than 2. Here we just use 2 of them. Somewhat frequent we'll use 4 rules instead of 3. That's usually the typical. Like I'd have to go looking to see if there's one where we use 5, but I don't think there's very many.
So is there like any set way you have to do the rules? Like, can you ever is there any? I don't know how to ask this, but it's like, is there never a rule that you can't start with? Like you can start with all these rules and kind of work from there.
What Max is asking is, I've got all these rules. Is there flexibility in how I work my way through the problem? And the answer is actually no. There's a couple of examples where you have some flexibility, but generally you have to make the right sequence of choices. And if you make a wrong sequence, you will step into a trap. You'll have the wrong answer. Yeah, it's a pre-programmed sequence. The trick is you've got to learn how to find it yourself. Like I can't say the sequence is always the same. It's not. The general pattern is always the same. It's like I was saying to Jacob, you've got to go find the correct menu choice, use that, and on the next line it's going to be a different menu choice, use that. So, 4 points. Anybody else? Ariana, please.
Would there be anywhere it's possible to use the same rule twice?
It's actually fairly common to end up using the multiplying constant rule more than once. It's common to use the power rule more than once. The other rules for our level of difficulty don't typically get used more than once. So, add subtract sometimes will pop up twice, but 4 points for Ariana. Cool. Other questions? Really good questions. Okay, I'm going to stop the video so we can post that.